All right, so welcome to week 7. We've finished chapter 4 on bioenergy. We're marching on through. We're not quite halfway through the book, and not quite halfway through the semester either, but we're on track. So we're going to move into hydroelectricity. Tim and I were just over at Sentinel High School, and they've got a really neat engineering class over there. So one thing they're moving in, they kind of got through some of the mechanics, gears and things like that, built some kind of simple machines, and now they're actually getting into energy and power. So we had a chance to show them some of the things. When we were there, they were going over wave energy, which we'll cover later. But while we were there, I got to show them the Gordon Butte project. And so this is a hydroelectric project. It's as you'll notice, there's no major river nearby, but there's enough water obviously to support some agriculture there. And what they're doing in Gordon Butte is really combining wind power, which is obviously driven by thermal gradients of the atmosphere, which is driven by the sun and the Earth's rotation, to provide energy security. So when the wind is high and demand is low, they're pumping uphill. When wind is low and demand is high, they're making electricity going downhill. And so as we move through the chapter here, Chapter 5 in hydroelectricity, we'll look at some of the scientific and engineering principles behind that. When I was giving my talk in Billings a couple weeks ago, there was a little bit of confusion or controversy about how powerful this storage facility is. I stated that it had an 800 megawatt capacity, and a few other people said no, it's a 400 megawatt system. Well, as it turns out, it's both. This facility has the capability to both store and produce electricity at the same time. So it can pump at 400 megawatts and make electricity at 400 megawatts. And you're like, okay, wrap your head around that one. I mean, obviously it's net zero, right? I mean, if it's pumping at 400 and producing at 400, the level of water in the facility doesn't change, right? I mean, it's going up as fast as it's going down, but that was the source of the discrepancy. Is there are actually two separate turbines inside. They spin in the same direction, so while one's pumping, the other one can be storing, and so. And you can sort of see the scenario, and that's a scenario where supply equals demand. I mean, you might have 400 megawatts of supply coming in and 400 megawatts of demand going out, thus making, it's an 800 megawatt facility, even though it's not making 800, it's doing the same simultaneously. So I hope the audience is listening for my explanation and conclusion, and hopefully that clears up the discrepancy. But Carl Borquist is the president of Absaraka Energy that's putting this together. It's a really cool project, and in a lot of ways the future in terms of how we're going to have nice big piles of gravity-rich water laying around instead of big piles of carbon-rich coal underground. So that's the analogy there. All right, so let's get into chapter 5. How are you all doing with that? I guess I gotta. Before we get into chapter 5, I just want to do one more thing here. We haven't launched summary 3. We'll do that in my office. I want to make sure that we're all on board with summary 3. I've got it here. It's not due yet. but I want to make sure we're all on the same page with that.
Isn't that one due
Yeah. And I haven't really looked at the papers for summary 2, but tell me what was your general impression for summary 2?
Wow.
It's a gnarly paper, isn't it? Yeah. One thing that I'm really trying to move towards with NRG 101 and 102 is that they actually become science electives for the university. I mean, right now, we see a relatively small number of students in the classes because it's just for energy technology students. But another thing that I noticed being over on main campus not too long ago, I was in the chemistry department, and I was looking at their composites of, their recent graduates, and they might only have like 6 or 7 graduates per year. I'm like thinking, well, how can chemistry only have 6 or 7 grads? I mean, but they do a lot of service courses. I mean, most people, to get your college degree, regardless of your major, you got to take some chemistry. So that's why. So it could be down the road that we see more students in 101 and 102 if my little proposals to have these be science courses take effect. Okay, all right. So summary 2 is behind us. We'll do a little summary 3 later. Problem set 1's coming in. So let's get into hydroelectricity, chapter 5. Yeah. Like I said, for whatever reason, I do just I just like these books. Oh, and I just recently got invited to provide a review for Bill Nye's upcoming book. I guess he wrote something, and they're like, oh, who the heck's out there? And Leighton, well, no one's ever heard of him before, but he'll be a sucker and read the thing and provide some. Bill Nye, if you haven't heard, he's kind of like trying to do a broad push for understanding the implications of climate change and energy sustainability. So he's the science guy. If you watch him on Dancing with the Stars, though, he got nailed by the judges. Like, Bill, what kind of hip action is that, man? It's pretty funny if you watch it. Yeah. So I'm trying to think of how in my review I sort of, ding him for his Dancing with the Stars, but then, praise him for his science. I don't know.
You're a scientist, no?
Yeah, something like, I think that they said, stick to the science, Bill. Yeah. All right. Hey, well, here's the big picture on hydroelectricity production. As we mentioned previously, hydroelectricity's primary energy source is from the sun, which causes thermal gradients to causes thermal gradients on the Earth. Thermal gradients causes changes in pressure. Changes in pressure cause wind. Wind can be used to pump water uphill. In our case, though, the sun's heating of water pumps water molecules actually into the air. That becomes a gravitational resource. The water backs up behind the dam, and then we can spin magnets and make electricity from it. Okay, so this is annual production, so world total electricity production. This is in terawatt hours. I'm a little surprised to see that it actually peaked, but if you remember, if you pay attention to that Shramsky paper, there was that green curve where right around 2010, 2015, we did sort of see a dip or a decrease in the energy per capita. And like we discussed before, that's one of 2 things. It's either poverty, meaning people don't have as much access to energy, or it's efficiency. We're able to do more with less. And we're sort of hoping that the latter is the case, right? It's sort of the happier future that we're hoping for. Okay, so this is just electricity. This does not include heating, transportation, that type of thing. Hydro is growing, but again, there's a sort of a limit to how many things you can dam up. I don't know if you've been reading the news or not, but it looks like China has purchased a large chunk of Ecuador and is undertaking a sort of, somewhat controversial hydroelectric project there. They're sort of damming up the headwaters of one of the highest waterfalls in South America, and, the whole habitat thing. I don't know if you remember, like the Three Gorges Dam and the last I don't know, I can't remember, this poor dolphin was the last dolphin, freshwater dolphin, anyway. So, there's no perfect solution, but that's where we are with hydroelectricity. Okay, now, since this book is Eurocentric, and more specifically British-centric, we're focusing on what's called the Galloway Hydros. So, and I'll just read this first little chapter here. The Galloway Hydroelectric Scheme on the River Dee in southwest Scotland makes an interesting study for several reasons. Initially commissioned in 1935, it was the first major UK scheme designed specifically to provide extra power at times of peak demand. Very similar to that Gordon Butte project that we just mentioned. It's 6 power stations, and we're looking at them right here in front of us, are controlled as one integrated system. Pretty impressive, that they sort of got their act together and did it as one giant engineering project. Several of its dams are on major salmon fishing rivers, raising environmental issues, common to many hydro schemes, and I mentioned dolphins in China as well. It is also technically interesting because significant differences between the site conditions and the power station locations mean that across the system several types of turbo generator are used. And what that means is, and what that comes down to, and I think I can explain that in relatively simple terms. When we're talking about hydropower, power is going to equal the force times the velocity. It's also going to equal the pressure in the system. Actually, let's write it this way: small p for pressure times the mass flow rate. So, in the case of a typical linear system, if you've got a lot of force behind something that's moving fast, it's very powerful. But in the case of a hydroelectric system, and again, every single power system is going to have an across variable and a through variable. And so the across variable means sort of force. I can do a little hand puppet on this. The across meaning force being across some space. So you can think of a tug of war, and that force being across space. And then the through variable is the velocity moving through something. So the top power, and I can just say this is going to be mechanical. So you can think of this in terms of a car transmission or a car driving through the air. Or in the case of hydroelectric, granted it's still mechanical, it's gravitational. So the pressure is how high the water is. So the higher the dam is, the more energy is stored in the system, and thus the more velocity, or in this case, the more mass flow rate you're going to get through the system. And I will make the concession for all of the sticklers sitting out there. This is not the exact equation. If you actually did the dimensional analysis on it, it's not going to come out exactly right. But this is the proper way to think about it. So, more pressure and more flow, and again, the mass flow rate just means that I've got this chunk of water right here, and how quickly is it moving through the system. So again, that's how you any power system is always going to have a pressure variable and an across variable, which is like pressure, like voltage, or in this case, like force, and a through variable, like in the case of electricity, would be current. But in this case, we're looking at the mass flow rate. Okay. So that's speaking to this last little sentence, seeing several types of turbo generator. Some are going to be high speed, low torque. Some are going to be low speed, high torque in order to maximize power. Okay, and in fact, the equation that's actually given here in the textbook, I'll go ahead and write it down. It says power in kilowatts equals 10 times Q times H. Now, if we had to match these variables up, what's the corresponding variable for Q in this other equation that I just wrote a second ago? What is Q?
Mass?
Yeah, it's the flow rate, yeah, exactly, yeah, that's exactly right. So it corresponds with this guy, and then the H for head, that's the engineering term for pressure, is that one. So you can, and then the 10, this is more or less the gravitational constant. And it's not given there, it's just given as a multiplier. Okay. Box 5.1 talks about capacity factor. It says CARS-FAD. Let's see where CARS-FAD is on this guy. So it says if the CARS-FAD power station with a 12,000 kilowatt capacity generates 30 million kilowatt hours of electricity, what is its capacity factor? So let's just do that math while we're sitting here. Okay. So let's hop ahead and just follow along with me here. It's nice to just write this stuff down. So box 5.1, we know that the capacity equals 12,000 kilowatts. Now, what's that measuring? Is that measuring energy or power? Measuring power. So that means going full out, it's a 12 megawatt system. I'll just write it like that too, equals 12 megawatts. How does that compare to Gordon Butte? Is it bigger or smaller? Way smaller. Gordon Butte, 400 megawatts. So, you know, we're Montana, got to do things big. So, I mean, 12 megawatts is nothing to sneeze at, but it's tiny compared to what's going on at Gordon Butte. So, let's figure out how much energy could be produced if it were running at 100% 24/7, 365. So let's just do that little bit of math. So we know that energy equals power times time. What do we know? Well, we know the power. We just wrote that down, 12,000 kilowatts. And can we figure out the amount of time in a year? I would hope so. So let's just go with that. So energy equals 12,000. And let's keep this in kilowatts and hours. Let's not dig down into the seconds regime. So 12,000 kilowatts. And now all we have to do is figure out the number of hours in a year, and that's given for us right here. So we've got 8760 hours per year. I'm doing it a slightly different way than the book is. Just, I think it's maybe a little more digestible this way. I'll pop that into Excel. So don't make any mistakes. And since the numbers are not going to show up that well on the desktop calculator, so we're looking at equals 12,000 times 8760. And what I like to do in Excel, sorry that's so small, let me make it a little bit bigger here. For me, being an engineer, it's easier for me to look at that. Actually, let's just do it this way. I'll show it in a couple different formats. So that's scientific notation. So this is going to be energy per year, right? Energy per year, and we know that the units, whoops, I'll change that. We know that the units are kilowatt hours. energy per year. That's also kilowatt hours, and we'll do the same thing here. Energy per year, kilowatt hours. Now I'm just going to change the format. Control 1, and I'm going to turn that into a number, 0 decimal places. I'll throw a comma in there. Okay, that's fine. I can see 105,120,000 kilowatt hours. Now, I'm going to put this in engineering notation. Actually, I'm going to change that back to scientific notation. I don't know why it changed. I'm going to do one more here and do control 1. And I think there's like a special, there's a custom. Okay, if you dig down in here, red, there's an engineering notation that's kind of fun. Let's try that one. Okay, so what that's done for us, this exponent is always going to be a factor of 3. So now we can sort of look at it and say, okay, that's 105 mega kilowatt hours. Kind of a funny way of saying it, but this, that engineers tend to think in, factors, kilo, mega, giga, et cetera, et cetera. Okay, so different ways to look at it. Now, to get to the capacity factor, so I'll just like 105 times 10 to the 6th. 105 times 10 to the 6th kilowatt hours, right? Because when we do, and that's per year, all of the units, the kilowatts, the hours, and the years survive, and there they are. Okay, now, the question said that it generates, this is going to be E gen, I can call this E capacity. E gen equals 30 million, so 30 times 10 to the 6th kilowatt hours. So the question is, what's the capacity factor? Was this thing running at 100%? No. The other thing to keep in mind, this is not the efficiency of the system. The efficiency is something else. It's like what fraction gets turned to electricity versus what fraction gets turned into heat. And in general, the hydroelectric is very high, above 90, maybe 95. Okay, so the capacity factor, I'll just call it C sub F equals E gen over E capacity equals 30 times 10 to the 6th over 105 times 10 to the 6th equals, and then I can just, so I'll just do 30, E6 right here, and then the capacity, CF equals that divided by that, ding, ding, and now we can take that again. That's kind of a weird looking number. It's in let's just change its format, control 1, and let's just put it as a percentage. 28.54, and that's what the book has. So that's, when dealing with problems, just take your time, take it slow, look at it in a few different ways, and there you go. There's the capacity factor. Okay, now, back to the textbook. Let's see how we're doing on time. We've got a few more minutes before we hit 30. Back to the textbook, table 5.1 shows the stations. So there's Drumjohn, Keemdoon, Carlsbad, Earlstrom, Glenley, Tongland. They show the head, they show the flow rate in cubic meters per second, then they show the capacity. So Kendoon is the largest at 24 megawatts, Drumjohn is the smallest at 2, Tongland has the greatest number of turbines at 3. So obviously some engineering in each one of these, what's the optimum number of blades, etc. Table 5.2 shows that they either have propeller or Francis turbine types, and we'll later in the chapter, we'll see exactly what those look like. Okay, here's a neat little shot, and I don't know, I think it's a good-looking building. And in fact, if you walk by the University of Montana's own power station, it's a well-appointed building. I mean, the brickwork's nice, there's windows, it's integrated with the surroundings. I mean, anyway, I like to look at this. That's the Carlsbad station and dam, and there's the little station where the electricity actually heads out to the grid. Environmental concerns, here's your fish ladder. I recently learned that some of the dams in Great Falls did not require this because the falls were too challenging for fish to make it up anyway, and there really were not fish populations above that prior to the installation. So once in a while, like, well, the fish weren't swimming up there anywhere. They weren't. Again, all these different factors go into decisions and how the technologies are deployed. Okay, so we've covered 5.1 and 5.2. My battery's running low, and we've got about 40 minutes left. So let's just take a break. We'll head over to my office, and then I think we can get through the next half of the chapter, and then we'll finish it up on Thursday. So we'll take a little break here.